So cool. Discovered the electron. That led to a whole bunch more questions, which is usually how things work. So there's negative electrons in the atom, then there must be something that's also positive. Because we knew that atoms are neutral, they don't have an overall charge on them. Well, so we've got positive and negative charges in the atom. How does this work? How do those particles fit together? Are there more particles in there besides these two? Is it just a jumble of more fundamental particles? Are atoms solid spheres, or what exactly are they? Is there some internal structure to them? So many questions. So you have to start somewhere. So Thomson started with what's known as the plum pudding model. Anybody ever had plum pudding? I haven't. It's a British dessert, right? We won't comment on British food. But the closest thing we have to it in the U.S. would be something like a blueberry muffin. Okay, so you've got this muffin, this bread cake kind of stuff, and then there's blueberries, and they're just kind of random inside. Okay, so this was his idea. We have to start somewhere. Plum pudding model. Okay, the electrons are like the blueberries, and this positive charge that must be there, but we don't know what it looks like, is the muffin part. So that was the idea. And so you come up with this idea, and then you have to test it. Well, before we can talk about testing it, we have to understand a little tiny bit about radioactivity. So radioactivity is when certain nuclei emit small energetic particles just spontaneously. And that was discovered at the end of the 19th century by Henri Becquerel and Marie Curie. And this allowed the scientists to probe the structure of the atom. The problem with studying an atom, which is like crazy small, is if you want to look at what's inside the atom, you need something that's even smaller that you can poke it with, basically. So there's three main types of radiation: alpha particles, beta particles, and gamma rays. The alpha particles have a positive charge on them. They are the largest of the radioactive particles. And radioactivity will be covered in Chapter 1 in Chem 1B. We just need to have an idea of what it is. So Rutherford was one of Thomson's students, and so he did an experiment in an attempt to confirm Thomson's plum pudding model. It didn't work. Turned out it showed that the plum pudding model was wrong. It's not what he set out to do, but it was a great discovery. So in the experiment, Rutherford directed these positively charged alpha particles at a very, very thin sheet of gold foil. So the plum pudding model predicted that we have mass and charge spread throughout the entire volume of the atom. We're predicting that these teeny tiny particles will just go straight through. They'll just shoot straight through. So this is an illustration of the setup. Here we've got the X-rays, the alpha particle generator. We're shooting these alpha particles at this really, really thin gold foil. And most of the particles went through with little or no deflection, which was expected. But some of them bounced off. This was not predicted. About 1 in 20,000 bounced back, and Rutherford said, this is about as credible, believable, as if you had fired a 15-inch shell, so like a cannonball basically, 15 inches, fired it at a piece of tissue paper, and it came back and hit you. Would you be surprised? You'd be in pain too, but you'd be like, wait, what? How could that happen? Right? Okay, so plum pudding model, not good. Let's come up with something else. So he developed a new model. So from this, he decided that matter must not be as uniform as it appears. Because what was predicted, that these little particles would just pass straight through. But what happened is most of them went straight through, but some of them bounced back. So there must be something in there that's really, really dense. And if your particle hits that, it bounces back. Anywhere else, it'll go straight through. So, it might be a little bit like, say, a volleyball net, right? It's got all these strings tied together, right? Relatively big holes. And then you've got an airsoft gun, little teeny plastic pellets, and you're shooting airsoft pellets at the volleyball net. Most of the particles are going to hit the holes and go straight through, right? But if your particle, if your airsoft pellet hits the string, it's going to bounce back. Okay, so this is not uniform. There's string that's dense, and then there's empty nothing in between. So that's kind of the idea. So this particle here was concluded to be the nucleus, and then the electrons are just around it somewhere. That was another problem to be solved later. So Rutherford came up with the nuclear theory of the atom, 3 basic parts. Most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. Most of the volume of the atom is empty space, and that's where the tiny negatively charged electrons are found. And 3, there are as many negatively charged electrons outside the nucleus as there are positively charged particles inside the nucleus. And they named those positive particles protons. So proton and positive both start with P. The protons are the positive charges. So this was great, but there was a problem. So hydrogen has 1 proton, and helium has 2 protons. So if you've got 1 proton and 1 electron, or 2 protons and 2 electrons, you would expect that the mass of helium would be twice as big as hydrogen, right? Because it has twice as many particles. But it was 4 times as big. What's going on there? Well, we'll spare you the details. But Rutherford and one of his students, James Chadwick, figured out that unaccounted for mass was due to neutrons. So these are neutral particles. Neutrons are neutral, protons are positive. So these are neutral particles that are inside of the nucleus as well. So neutral particles, no electrical charge. The mass of the neutron, though, is very similar to that of a proton. So where a hydrogen atom has 1 proton and no neutrons in its nucleus, the helium atom has 4 particles, 2 protons and 2 neutrons, and that's why it weighs 4 times as much. Problem solved. So the nucleus is extremely dense. That's an understatement. Over 99.9% of the mass of the atom is in the nucleus, and yet it occupies very little space. You could think of it a little bit like a cloud. The electrons are a bit like the water droplets in a cloud. So you can see a cloud, or you can see the fog in the winter, right? But you can also just walk right through it. Yeah? So why can't you see through it? Because those little particles, those water droplets, are spread out in this big volume, and they're blocking light from going through, which is what makes fog so dangerous, right? But the fog, the cloud, is mostly empty space. Those little water particles don't really weigh much of anything, right? And yet we can see them. So we learned that matter is much less uniform than it appears. There's an awful lot of empty space in matter. So if you had a nucleus the size of a period, printed period, little teeny tiny thing. The electrons would be 10 meters away. So here I have a meter stick. Okay. So let's start at the door. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if the nucleus, the size of a period, was at the door, the closest electrons would be over on the other wall of the classroom. What's in between? Nothing. So then you think about, some of these science fiction things and about matter passing through matter, and you're like, well, heck, maybe we could figure that out, right? If you had a grain of sand that was just nuclei, without that empty space in the electrons, a grain of sand, it would weigh 11 million pounds. A grain of sand, 11 million pounds. That's how dense the nucleus is. There's just so much empty space in matter. Anybody have any questions? These things are really incomprehensible. I mean, you can say, okay, yeah, but can you really grasp that? I don't know. So you've seen scaffolding they put up on the outside of a building, like our new science building. It's called a scaffolding, which is like platforms and rails and stuff so that workers can work on the outside of the building. So if you had scaffolding the size of a football field, this also very much resembles the play structures that we had when I was in elementary school. They were made out of metal pipes and they were on asphalt. And yes, we fell off and landed on our heads. And most of us lived, right? So we've got this scaffolding as big as a football field. That's really big. There's a football field, which is over there, right, close stadium. And 100 stories tall. Most of that's empty space, though, right? And if you're this guy standing down here, you can see straight through, right? But when you zoom out, when you get away from that, say outer space or a very high airplane, when you look down at that, it's going to look like a solid object because the difference in the open spaces and the solid spaces becomes indistinguishable as you get further away. So if that was the atom, 100 stories tall, the size of a football field, the nucleus inside would be the size of a green pea. Mostly empty space. But when you knock your knuckles on the table, so we've got mostly empty space hitting mostly empty space, and yet they don't go through each other, right? But they don't fall into each other either. It'd be like taking the two big scaffoldings and crashing them together. They're not going to go through each other either. So matter appears to be solid to us because the variation in density is too small for us to detect. Any questions?